Picture this. It's May 1945, and you're standing on the flight deck of the USS Enterprise in the Pacific. The Air Boss has just launched 30 Hellcats and Dauntless dive bombers toward Japanese positions. In 2 hours, they'll return low on fuel, some damaged, their pilots exhausted, but there's a deadly problem waiting for them. The flight deck, an 872-foot-long strip of steel, has only one way in and one way out. Every carrier in World War II functioned like a lethal game of musical chairs. Returning aircraft had to land one at a time from the stern, catch an arresting wire, and taxi forward to park near the bow. It sounds simple, but each landing took roughly 90 seconds, and with 30 planes circling overhead, and only 20 minutes of fuel left, the math was grim. That's 45 minutes to recover all aircraft to long. The last pilots landed on fumes, and if even one missed the wires and crashed, everything stopped. Deck crews had to shove wreckage overboard while the rest burned fuel above, watching their gauges sink toward empty. But the real nightmare came after recovery. Once all aircraft were aboard, they sat wingtip to wingtip, from bow to stern, fully armed and fueled. The deck became a parking lot loaded with bombs and aviation gas. Want to launch another strike? You couldn't, not until deck crews manually rearranged every plane, process taking another hour. For 60 to 90 minutes after landing, the carrier was useless. Admiral Mark Mitcher of Task Force 58 called this the deck cycle problem, and it was strangling American naval air power. His ships could carry around 100 planes, but because of straight deck geometry, they could manage only one major strike per day. The Japanese faced the same issue. At Midway in June 1942, their carriers, Akagi, Kaga, and Soru were caught with decks crammed with refueling planes and were destroyed because they couldn't launch or land. Admirals realized the terrifying truth: battleships could fire continuously, but a carrier limited to one strike every 6 hours was a sitting duck. In theory, an American carrier would get one blow before submarines or enemy surface ships closed the distance. The straight deck design wasn't incompetence. It was inherited convention from the 1920s, when nobody had imagined a better way. But the loss of pilots, many running out of fuel above their own ships, proved the design's fatal flaw. Pearl Harbor in December 1941 showed the power of carrier warfare, but it also exposed its weakness. After launching 2 waves of 353 aircraft, Admiral Nagmo's decks were so clogged by AM that he couldn't launch a third strike on Pearl's vital fuel and repair facilities. Clearing and respotting would have taken 3 hours' time that could have left him open to counterattack, so he turned for home, leaving the job unfinished. The Americans learned the same hard lesson at Midway 6 months later, when the Japanese decks were frozen in the rearm cycle. In just 5 minutes, dive bombers from the Enterprise destroyed 3 carriers because the enemy couldn't clear their decks. After that, navies began measuring something called deck cycle efficiency, or how long a carrier was useless between strikes. The results were brutal. During Guadalcanal, the Yorktown averaged 93 minutes between recovery and launch. Saratoga needed 108 minutes at Santa Cruz, and Japan's Shokaku required over 2 hours. Carriers spent more time rearranging aircraft than fighting. Enterprise Air Group Commander Wade McCluskey wrote in early 1943 that, "We're built for one-punch fights, but we're in a 15-round boxing match." He calculated that whichever side launched first in an open ocean clash would almost always win, since the other would be trapped mid-recovery. Naval warfare had devolved into a quick draw contest. By mid-1943, the U.S. Navy had enough Essex-class carriers to rotate duties: one launching, one recovering, one rearming, but that meant 3 carriers were needed for the job one should have done. Commander Joseph Clifton recorded during the 1944 Battle of the Philippine Sea that it took 97 minutes to recover 226 aircraft, and 5 pilots ditched for lack of fuel. It wasn't sustainable. As carriers grew larger, capable of holding up to 100 planes, they still couldn't use them efficiently because their decks were stuck in 1920s geometry. While American carriers fought in the Pacific, the Royal Navy quietly worked on a fix. operating in the stormy North Atlantic with smaller decks and cramped hangars. Captain Matthew Slattery of HMS Illustrious realized in 1943 that conventional straight-deck operations would never achieve efficiency. He experimented with the radical idea of letting planes land while others sat parked forward. His crew painted a white line down the port side to create a narrow landing lane bypassing parked aircraft. The first test worked once before disaster struck, when a seafire clipped a parked swordfish. Still, Slattery had proven a crucial point: you didn't need the full deck width for landings. Then came physicist Dennis Campbell from the Royal Aircraft Establishment. Studying efficiency in late 1943, he realized the flaw. Carriers treated decks like highways, one lane, one direction. But if you angled the landing area like intersecting railway tracks, you could handle takeoffs and landings simultaneously. His January 1944 proposal called for cutting the aft flight deck 5 degrees to port, so planes could land at an angle, catch arresting wires, and taxi off while others launched from the bow. Admirals were skeptical, but HMS Triumph was chosen for a test. In August 1944, engineers painted an angled strip and shifted arresting gear. No major rebuild, just paint and repositioning. Test pilot Eric Winkle Brown later said landing on the angled deck felt like touching down on a turning ship, but it worked. He landed, cleared the path in 45 seconds, and another plane launched instantly. For the first time, both operations ran at once with zero interference. The Royal Navy kept testing through 1944-45, improving results, though the 5-degree angle still caused congestion. The war ended before refinement, and the idea sat forgotten in files until 1951, when U.S. Navy test pilot Commander Walter Boone revisited it. With jets arriving, experts warned that carriers were obsolete, their decks too short and narrow for fast aircraft. But Boone, after reading the overlooked British reports, saw what others missed. The angle just needed to be greater so that if a plane missed the arresting wires, it could power up and take off safely. The British had been thinking about traffic management. Boone was thinking about survival, and his insight would soon change carrier aviation forever. Boone was thinking in terms of physics and failure modes. He realized that if the deck was angled 8 to 10 degrees, a pilot who missed the arresting wires, a bolter, could simply throttle up, climb away, and circle back for another attempt. No crashes, no wreckage blocking the deck, and no dozens of planes burning fuel while waiting for the mess to clear. In March 1951, Boone pitched his idea to Rear Admiral Apollo Sosick at the Naval Air Test Center in Patuxent River, Maryland. Sosick's response was short and simple: prove it. Boone and his team soon got their chance. They took USS Midway, then in Norfolk, for maintenance, and painted an 8-angled landing area on the flight deck, repositioning the arresting gear accordingly. The geometric change seemed simple, but its implications were revolutionary. The new layout created 2 independent runways on a single ship, a straight catapult track running bow to stern for launches, and an angled landing strip veering off to port for recoveries. For the first time in naval aviation history, a carrier could launch and land aircraft at the same time. The first tests took place in July 1951. Boone himself flew the initial approach in an F-9F Panther, coming in at 145 knots toward a deck that appeared to be sliding away from him. He caught the third wire perfectly, taxied off to port, and while he was still rolling, another Panther was catapulted from the bow. 30 seconds later, a third aircraft trapped on the angled deck, then another launch, another recovery. Operations that once took 90 minutes now flowed continuously. In 18 minutes, the test team recorded 12 landings and 12 launches, an evolution that would have taken over an hour on a straight deck. But the defining moment came when Boone deliberately bolted on the 7th approach, missing every wire. On a traditional carrier, that would have been catastrophic. He'd plow into parked planes and likely kill crewmen. On the angled deck, he simply added throttle, lifted off, and came around again while the deck crew barely reacted. He trapped cleanly on the next pass. Sosick, watching from the island, instantly grasped what he was witnessing. The angled deck didn't just improve efficiency, it eliminated the deadliest failure mode in carrier aviation. By August, the tests proved the system worked with multiple aircraft types, and by September 1951, the Navy's Bureau of Aeronautics was drafting plans to retrofit the entire fleet. One test pilot and a can of paint had just doubled America's carrier striking power. But proving the idea with paint was one thing, making it permanent was an engineering nightmare. It would take 3 years, hundreds of millions of dollars, and a total rethink of carrier design. The challenge wasn't just cutting the deck at an angle. Every system aboard had been built around straight deck geometry for 30 years. Change one thing, and everything else had to change too. The first issue was the island superstructure. On straight deck carriers, the island sat midship on the starboard side, perfectly aligned with the landing path. But with an 8-angled deck, incoming aircraft were now flying directly toward the island before touchdown. The approach path literally crossed where the island stood. Naval architects at the New York Naval Shipyard spent 6 months in 1951 running calculations. Could they move it, shrink it, or somehow make it invisible to pilots? In the end, they compromised, shifting the island slightly aft and widening the port side deck to accommodate the angled landing area. It required cutting into the hull and reinforcing the frame structure, putting each carrier in dry dock for 4 months of structural work. Next came the arresting gear. The hydraulic systems that stopped aircraft were built perpendicular to the ship's centerline, embedded within the deck. Angling them required a total redesign, rerouting hydraulic lines and rebuilding below-deck compartments. Grumman engineer Robert Decker estimated that each retrofit meant replacing nearly 40% of the arresting system. USS Antietam's conversion alone consumed 11,000 man-hours just for that work. Then came the catapult challenge, which turned into an opportunity. The Navy had been testing powerful new steam catapults, and the angled deck project provided the perfect reason to install them. Commander C.C. Kirkpatrick, overseeing Antietam's overhaul, realized that steam catapults on the bow, combined with angled landings aft, meant carriers could now launch and recover heavy jet aircraft simultaneously. But installing steam systems meant cutting deck plates, running steam lines from the boilers, and constructing machinery spaces below decks, transforming what began as a deck geometry fix into a full-blown rebuild. Even the new optical landing system, the mirror landing aid, posed problems. Developed by the British in 1952, it used a gyro-stabilized mirror and light array to show pilots their glide slope. Calibrating it to the new 8-angle proved tricky. Lieutenant Commander J.R.P.N. Lamb, the U.S. test pilot evaluating it aboard Antietam, crashed twice early on because the mirror's placement gave false readings. Engineers had to move and recalibrate it 3 times before it worked correctly. Between 1952 and 1955, the Navy converted 13 Essex-class carriers to the angled deck system. Each refit cost between $8 and $12 million, significant when the ships had originally cost $17 million apiece. USS Bennington entered Norfolk Naval Shipyard in January 1954 and didn't emerge until September. USS Hornet's retrofit took 7 months. These weren't mere modifications, they were structural overhauls. Crews cut away sections of the original deck, welded in new framing, and rerouted nearly every major system. The ships that returned to service were fundamentally different vessels, even if they looked the same from afar. When USS Antietam left Norfolk in December 1952, she became the world's first operational angled deck carrier, sailing straight into the Korean War to prove whether Boone's revolutionary idea would survive under combat conditions or collapse under fire. Within the Navy's leadership, opinion was divided. Half believed this was the future of carrier aviation. Half saw it as an expensive experiment that could kill pilots. Antietam had 4 months to prove them wrong. She arrived off Korea in January 1953 and immediately began flying combat sorties against North Korean and Chinese targets. Commander William "Will" Cisco, the air boss, kept meticulous records. He knew the Pentagon was watching. In the first week, Antietam launched and recovered 68 sorties in 12 hours. That might not sound dramatic until compared with her sister ship, USS Kearsarge, operating 50 miles south with a straight deck. Kearsarge managed only 39 sorties under identical conditions, same aircraft, same missions. The angled deck had boosted combat output by 74% from the same hull. Deck availability became the single most telling statistic in evaluating the efficiency of the new angled deck system. On straight deck carriers operating during the Korean War, decks were available for landing only about 42% of the time. This meant that pilots launching for strike missions faced nearly even odds that the flight deck wouldn't be ready when they returned. If the deck was closed, they had to waste precious fuel circling or divert to emergency fields in South Korea. On Antietam, however, the introduction of the angled deck changed everything. Availability surged to 79%. For the first time, pilots could rely on having a ready deck waiting for them. That statistic sounds abstract until you consider the pilot in the cockpit watching the fuel gauge drop. Lieutenant James Miker, flying F-9F Panthers off Antietam in February 1953, saw firsthand how that angled deck saved 3 lives in a single afternoon. In one case, a skyraider returning from a close air support mission took heavy battle damage and came in too fast, boltering through all 4 arresting wires. On a traditional straight deck, he would have slammed into the parked aircraft forward, likely killing himself and several crewmen. On Antietam's angled deck, he simply flew off the port side, climbed out, dumped fuel to lighten his load, and trapped safely on the next pass. Later that same day, another emergency struck. An F-9F Panther returned with the hung bomb that had failed to release and was now live. On a straight deck, landing him would have been unthinkable, too dangerous with aircraft parked forward. On the angled deck, though, the landing area was clear. The pilot landed immediately and safely. The third incident involved a pilot suffering spatial disorientation who approached far off the centerline. He touched down dangerously close to the port edge of the flight deck, an impact that would have sent him straight into the island structure on a straight deck. But on Antietam, the angle of approach brought him close to the normal glide path, and he trapped without incident. By March 1953, Commander Sisko's operations logs showed Antietam averaging 89 sorties per day compared to just 47 on straight deck carriers, a staggering difference. The Navy sent Captain John Crommelin to observe and report his findings. His message to the Chief of Naval Operations was blunt: angled deck increases striking power by a minimum of 85%. Every carrier not modified is fighting at half capacity. Recommend emergency conversion of all fleet carriers immediately. That report silenced remaining skeptics in Washington overnight. What finally cemented the angled deck's dominance was a new operational metric introduced in April: mission effectiveness cycles, measuring how many complete launch recovery rearm relaunch sequences a carrier could execute in 24 hours. Straight deck carriers averaged 2.3 cycles per day. Antietam achieved 4.1. She wasn't just more efficient, she was fighting like 2 carriers in one hull. The simple geometric innovation Boone had demonstrated with the can of paint in 1951 was now proven with combat data in Korea, under fire and real operational stress. The success ended all debate. By late 1953, the U.S. Navy committed not only to retrofitting existing carriers, but also to designing an entirely new class built from the keel up around the angled deck concept. These would be the Forrestal-class supercarriers, the first warships in history designed with the angled deck as their foundation rather than an afterthought. Every other system, propulsion, armor, weapons, hangar layout, even crew quarters, was engineered to maximize what that 8-degree offset could deliver. When USS Forrestal launched in December 1954, the leap forward was immediately visible. The angled landing area was no longer just painted lines, it was integrated into the ship's very hull, with reinforced deck plating rated for jet aircraft impacts. The island was pushed farther aft than on any previous carrier, clearing the pilot's approach entirely. 4 steam catapults, 2 on the bow and 2 on the angled waist, allowed Forrestal to launch 4 aircraft every 60 seconds while simultaneously recovering others. Her theoretical sortie rate reached 170 flights per day, nearly double the best performance of any World War II carrier. Captain Roy Johnson's 1955 shakedown trials off the Virginia Capes confirmed it all. In one test, Forrestal's air wing launched a 40-plane strike, recovered 32 aircraft from the previous mission, and launched another 20-plane combat air patrol, all within 47 minutes. 3 distinct operations, catapult launches, arrested recoveries, and deck handling were running at once, perfectly choreographed by geometry. The strategic implications were enormous. Soviet naval planners had long assumed that carriers were vulnerable during flight operations, catch them while launching or recovering aircraft, and you could cripple them. But the Forrestal-class ships shattered that assumption. These carriers were never truly exposed because they were never truly idle. Soviet Admiral Sergei Gorshkov's 1956 assessment concluded bleakly that NATO carrier groups centered around these new ships could maintain continuous strike capability, and that the Soviet surface fleet had no viable counter to supercarriers capable of launching 100 sorties a day indefinitely. By 1959, 4 Forrestal-class carriers, Forrestal, Saratoga, Ranger, and Independence, were operational. Each carried around 90 aircraft and could sustain sortie rates equal to 3 World War II carriers combined. During NATO exercises in 1960, Forrestal's air wing flew 147 sorties in a single day, including night missions. Even aircraft maintenance became more efficient. Where straight deck carriers had to pause operations to service planes, the Forrestal's forward deck park remained stable and accessible throughout flight cycles. The angled deck had done more than changed the shape of a ship, it had permanently rewritten the geometry of sea power. The introduction of the angled deck didn't just change how aircraft landed, it changed how nations thought about sea power. The doctrinal shift it enabled was profound. Before angled decks, carrier groups were forced to operate far from enemy threats because they required long recovery windows between strikes. They needed space and time to land aircraft safely. But the Forrestal and her sister ships erased that limitation. These new carriers could defend themselves even while conducting offensive operations, launching fighters, recovering bombers, and refueling the next strike wave all at once. Vice Admiral John McCain, JRB, described it in 1961 as rolling thunder capability, a phrase he meant literally. For the first time in history, the carrier had become a platform for continuous, uninterrupted air power projection. One innovation, one simple geometric shift, had created a weapon system that would dominate naval warfare for the next half-century. Walk onto any carrier deck today, whether it's the Nimitz class or the newest Ford class, and you're standing on the same geometry that Commander Dennis Boone first painted on the Midway in 1951. The 8-degree angled landing area remains. The catapult layout is unchanged, and the optical landing system still sits port side of the angled deck. 74 years later, no one has found a better solution, because the original one worked perfectly. That almost never happens in military technology. The USS Gerald R. Ford, commissioned in 2017 as the most advanced warship ever built, cost $13 billion and introduced electromagnetic catapults, advanced arresting gear, and a nuclear reactor capable of powering the ship for half a century without refueling. Yet her flight deck layout, the 8-degree angle, is identical to Forrestal's from 1955. The Ford can launch and recover 33% more sorties than the Nimitz class. Not because the geometry changed, but because her electromagnetic systems cycle faster and crews work more efficiently. The fundamental design that enables simultaneous launch and recovery hasn't changed, because it doesn't need to. The physics still work. Modern carrier operations now run at a tempo that World War II admirals would have considered impossible. During Operation Inherent Resolve against ISIS in 2016, the USS Dwight D. Eisenhower maintained an average of 75 sorties per day for 7 consecutive months. Across that campaign, Her air wing executed 12,000 combat missions without a single operational loss caused by deck availability or recovery failures. Pilots launched knowing that the deck would be ready when they returned, the same confidence Antietam's aviators had felt back in 1953. The angled deck had permanently removed an entire category of fear from carrier aviation. What truly proves the innovation's power, however, is its universality. Every major navy on Earth copied it. When China constructed its Liaoning and Shandong carriers, both featured angled decks. India's INS Vikramaditya has one too. Even smaller amphibious assault ships, like America-class and Britain's Queen Elizabeth-class vessels, ships that use vertical landing jets and don't technically require angled decks, still incorporate the geometry because it dramatically improves deck flow and aircraft handling. The principle outgrew its original purpose and became a universal standard for any vessel operating fixed-wing aircraft. The concept even outlasted the technology it was designed for. Boone's 1951 design focused on early jet aircraft. Yet the same 8-degree angle works flawlessly for today's fifth-generation stealth fighters, like the F-35C, and will work just as well for the unmanned combat aircraft of the 2040s. The geometry isn't tied to a particular plane, it's tied to physics itself, to the act of landing a fast-moving aircraft on a moving platform at sea. As long as carriers exist, the angled deck will remain. There's something profoundly elegant about that. A simple 8-degree rotation solved a problem that had once seemed insurmountable, one that admirals thought would demand entirely new ships or unimaginable technology. No exotic materials, no computers, no breakthroughs from secret labs, just a change in geometry that suddenly made everything work. Commander Boone probably never realized he was designing the blueprint for the next century of naval aviation. He only wanted to save pilots' lives and make carriers more efficient. But that's how the greatest innovations happen. Solve one problem perfectly, and you end up shaping the future. Stand on a carrier deck in 2025, and you're standing on a piece of 1951, thinking an idea so effective that nobody's managed to improve upon it, because nobody's needed to. The angled deck doubled carrier striking power, eliminated the deadliest failure mode in naval aviation, and became the foundation of 70 years of American dominance at sea. Not bad for an idea that started with nothing more than some paint and geometry.